Sorry to interrupt. Can I tell where he can see that chat section?
Actually, chat is on the top. If you see just below people, between people and reaction, in our window, it is showing on the second one, top.
In that bar where we can raise hand, उसके side में ही आ रहा होगा show participants. When we click on that, then we can see that people's chat.
Okay.
Still, I cannot. There's something wrong. No worries.
So, good evening, all participants. Today we are with our sixth session of this faculty development program on innovation and challenges of energy storage technologies. Our first week is having this last session in online mode. And today we have with us Dr. Sanjeet Dwivedi sir, and he will be discussing on the green hydrogen, its role on energy storage and grid stabilization. I would just like to introduce sir. He is a PhD holder from IIT Delhi, and he is one of my senior. We are from the same lab. So it's a proud privilege to have him on our expert panel. Dr. Dwivedi is a fellow of IET UK, working as Senior Technology Manager in Green Hydrogen Danish MNC Everfuel. Prior to this, he was Senior Research Leader at Danfoss, Denmark from 2008 to 2021. And before joining Danfoss, he was with Sagar Engineering College. In between, he was with Larsen and Toubro, electrical engineer and infrastructure company in India between 91 and 92. Then electrical engineer in CPW, Government of India. He worked as senior faculty member of the Department of Technical Education, MP, India in 93 to 2006. And while his stay at Government Engineering College, Sagar, between 2006 to 2008, he was Dean R&D there. Dwivedi sir is having two master's degrees. One is ME. He is a gold medalist in power apparatus and drives from IIT Roorkee. And second one is from the South Denmark University. He is MSc Engineering in Innovation and Business from South Denmark University. And he has completed his executive leadership education from MIT Boston also. He was honored with adjunct professor at Curtin University, Perth, Australia between 2016 to 18. He is a member of faculty board of South Denmark University in the Innovation and Business Department. And at present, he has authored more than 40 technical papers and holds 11 international patents, 3 business, trade, and 3 books of engineering research published by Academic Press UK and IET Press UK. He is an advisory board member of the International Journal of Power Electronics, IJPE, commonly known as Inter Science Journal, and associate editor of IEEE Transaction on Industrial Electronics. He has delivered a lot of invited talks in several IEEE and European Power Electronics conferences around the globe. And he worked as technical editor of IEEE ASME Transaction on Mechatronics and associate editor of IET Power Electronics, associate editor of Korean Journal of Power Electronics, JPE. He is recipient of Merit Award from Institution of Engineer India 2006 for his research publication on permanent magnet machines. He was also awarded with 9th Man on the Moon Global Innovation Award from the CEO and President of Danfoss in 2015. And he is a winner of another prestigious award, IETE Bimal Bose Award in 2017 for his outstanding contribution in power electronics and drives. So there are many things to his credit, And we are fortunate that we are having him with us to discuss on the recent development on the hydrogen fuel based systems. So I request Dwivedi sir to please take over the dais and now have a discussion with the participants.
Thank
Please,
you
sir.
very much. Thank you very much, Professor Chauhan, for such a nice introduction. I'm indebtful to you for kind words. So there are some ground rules for presentation. So whenever participants have any problem, as we discussed earlier, please raise the hand and we will stop. And I have planned this lecture, and then in between there were 2 breaks, where in these breaks we will do some numerical problems and these exercises, so to know how to calculate how much hydrogen is needed for our trip, as well as how much storage capacity we need. So they will be along the way. And then lecture is we are talking about mostly about green energy sources, their comparisons, and then deep dive into hydrogen. And in the end, we will see that how green hydrogen network can help us to stabilize our grid, and country like India, where we are aiming 100% renewable energy by end of 2030. There, this green energy infrastructure can pave a way, and it will be a complementary with the national power grid, and it will strengthen the grid and without necessity of investing money in the power grid infrastructure. So with these initial word, I'm sharing my screen. Please let me know when you see it.
Yes, sir, it is visible.
Okay. And I'm thankful for administration of MANIT Bhopal, and particularly electrical department, and Professor Chauhan and Professor Dwivedi for this invitation and opportunity to talk some of the recent technological development in the green hydrogen. So I will skip this portion, but this is my email. So if participants are interested in connect with me, or they are having any question, any follow-up, they can contact me, Sanjeet @ almuniit.ac.in. This is the place Kolding. It is a middle-sized town in Denmark and located in centrally in the Denmark. And its area is Uland. And this is the very beautiful picture of city center, where we can see the lake and the buildings around there. This is the headquarter. This is the place where I'm working. This town name is Henning, and there is a farm close to this town where my company Everfuel, which is a hydrogen full value chain company, starting from hydrogen generation to storage, distribution, and then owning the distribution network. So they are in full value chain of hydrogen network, and they are located in near Henning, in a farm, and they are also exist in Fredericia. That is the three-Kent area and very big industrial hub in Denmark.
Ah, sorry. Hello.
My outline of my presentation is like that. We will talk about green technologies. We will go through with some comparison between different green energy sources, such as solar, wind, biofuel, and green hydrogen. Then we will review hydrogen as an energy storage element. What are its advantages? What are its uniqueness? And why the world, and as well as India, is aiming from hydrogen economy in less than maybe in few years, maybe 4 or 5 years, we are looking for independent hydrogen economy. World is also doing that. Then after this, we will have a short exercise just before the break or after the break. And then we will deep dive in trends in solar and wind energy research, what is going on around the world, and what need to be done in this solar and wind energy area. Then finally, we will look into role of green hydrogen on grid stabilization and how it can help. Then again, we are having a short exercise and then conclusion. And after, if time permit, we will take multiple questions. And if time not permit, please shoot your question to my email and I will try to reply you and connect with you. So why green technologies? In 2015 Paris Agreement, nations around the world, they are agreed that rapid decarbonization, that is the need for present world and it to present the dangerous impact of, to prevent the dangerous impact of climate change. Then again in 2018, the Intergovernmental Panel on Climate Change, IPCC, they bring a report that global warming of 1.5 degrees centigrade, which was saying that there is a need to cut greenhouse gas emission. There is a necessity which this report bring, but it was seen more urgent than previously thought. So window of opportunity is closing fast for a meaningful action to save the planet Earth, to limit the planet Earth increase in temperature, and to counter the global climate crisis. Therefore, policymakers, they must increase their effort to reduce or eliminate emission in all economic activities. Options that would deliver only partial emission reduction are not sufficient. And then we see that driving this need for green hydrogen and green energy. The full decarbonization of some industry and transport subsector is technically and economically challenging. We know that. And the current number of solutions is limited. And we need innovation here. And these sectors, especially these sectors, they are hard to abate sector. There is, however, a common solution for some of these hard to abate sector. For example, hydrogen produced with renewable energy, also known as green hydrogen, can be a viable solution. And the whole world is moving towards that direction. Green hydrogen can be used as a feedstock for the production of chemical, fuel, fertilizer, steel, and directly as a fuel also. So why green energy? What are the alarming issues of climate change? As I stated earlier, the window of opportunity is closing fast for meaningful action to limit the planet increase in temperature and to counter the global climate crisis. We know that we can define the green energy and why we need it because of the environmental issues and carbon emission, carbon dioxide emission, and global warming. Energy systems worldwide are undergoing a major transformation towards the widespread use of green energy. The electrical power system in a sustainable future will augment the centralized and large grid dependent system of today with distributed small scale, small grid based energy generation system. So forget about this 1,000 megawatt NTPC coal-fired plant no longer because they are now trying to convert this. There were some. I was looking on some tie-up with Cell and NTPC. They were trying to convert their gas turbine with hydrogen firing gas turbines. So even their existing network is converted to this green energy based generating station. So they are these big uh, powerhouses with fossil fuel is the talk of past days. To achieve this, world will increase and adopt in renewable energy sources, solar, wind, and then their application in terms of fuel cells. And power electronics is essential for harnessing energy from solar, wind, fuel cell, or other green energy sources. Converter, inverter, and solid state transformer, they are the must. So be in our community of power electronics, we must be proud to say that we are helping for this the energy transition of the world and saving the planet. We are the savior. And electrical drive that play an important role in increasing energy efficiency of electrical power generated worldwide by conventional or green energy sources. So what are the future green energy system? The future energy system must necessarily deliver on the three dimensions. First one is the providing safe, secure, and reliable energy while delivering access to all energy consumers. Supplying energy at affordable prices and assuring sustainable development. And looking on these requirements, we only rely on the renewable energy sources like wind, solar, hydro, and geothermal, and similar to that. And these future green energy system, this will involve, in order to develop these future green energy system, this will involve massive changes in technical and organizational level, together with tremendous technological upgrade in different sectors, ranging from the energy generation and transmission system onto the distribution system. Of course, they will require these organizational level changes and technological upgrade. But do you know that how much uh, uh, total energy production in India is coming from renewable energy? Say in full number 400 gigawatt of energy produced today, how much is coming from the renewable energy? It is unbelievable. It's more than 60%. And our leader, our country leader, they are all looking for 100% renewable energy in next 4 years. So, but whole world that's transforming themselves towards this direction. These actions constitute a huge science and engineering challenges and demand for expert knowledge in the field to create solution for sustainable energy system, where energy supply and demand side and in the infrastructure to support this mismatch between supply and demand must be made. And this must be economically, environmentally, and socially viable by meeting high security requirement. So if we look on green energy system for future, it's no longer a centralized power station as it was in past. But instead of it, we can see in this diagram that this generating station that can be a small wind power plant or a small solar power plant or a microhydral plant. And it need not necessarily connected to the national power grid. It can feed the local load or it can feed the electrolyzer plant where green hydrogen is generated, and that can be carried in the pipe network, in a gas pipeline network, or it can be with the trailer or container. It can be moved from one place to another place. So we can see that, and not we don't have this model that generation, transmission, and distribution, but the utilization it utilizes some part of this network. They can also come off with feeding power to this network. So we need a special consideration for the stability of the grid, and then that can be only augmented that when we incorporate other than our existing customer, we can take that electrolyzer plant as a load. So we can ramp up the hydrogen production and ramp down the hydrogen production in order to keep stable the electricity. This is very promising slide. It is showing you what are the power generation cost by different energy sources. In our books, in a traditional way, for many decades, we were saying that solar and wind, that is far costlier compared to coal and our gas-based power station or conventional power station. But time is now over, and already solar and wind that is quite cheaper compared to conventional power station. So if you look on these numbers, you can find that solar is you get the $43 per megawatt hour. This is and gas is 52 megawatt per hour, megawatt hour. Coal is $65 per megawatt hour, and of course there is a extra cost for installation, but as a whole, the viability of the project with the renewable energy sources, that is far cheaper than conventional power sources. So when we are having these green energy sources and we need to connect them, and then we need a smart grid. And in very simple word, we can define this smart grid as a, this is local, so it creates energy for itself or nearby customer. It is independent, so it can disconnect from the central grid and operate by itself. And it is smart and intelligent. So the central brain or microgrid controller is where the intelligence originates. So we can see it here that this is the solar PV or utility plant. It can be connected or disconnected to the microgrid. And this grid can have other type of generating sources like solar here, and then storage system, and then another wind source, and then another this EV, and then we are having combined heat and power units which are connected here. Then this microgrid is connected with the energy market and also with the weather forecast. And not to forget that this individual microgrid, small microgrid, is connected with other microgrid in parallel in order to have reliable source of green energy. And this is the model which is also supporting the future smart cities also. So how can we secure green energy sources for next generation? If we look towards the annual world energy consumption, then we can see that we need in 2009, these are the some numbers from previous year, and there are predictions also. So in 2009, total energy consumption of world was 16 terawatt year per year. You know that kilowatt hour, then you can convert to kilowatt days or kilowatt year, and then kilo you convert to mega, and mega to tera. So you can see that how big this number in energy consumption. So in 2009, it was 16 terawatt year energy consumed in whole year, and there were 75% increase that was assumed between 2009 to 2015, and requirement in 2050, that is 28 terawatt year per year. So how is our energy reserve? Our total fossil fuel energy reserve is, in terms of coal, 900 terawatt year, uranium 90 to 300 terawatt year. So how many year we can run with coal with 30 year, um, and maybe 10 year with 10 to 20 year with uranium, or natural gas, it's 5-7 year like that, oil maybe 8 year, and kind of prediction. Hydropower station, they are renewable, and they can provide you 3 to 4 terawatt year per year. So there is no limitation, and we can get continuous energy from there. Wind, that is also having potential to provide us 25 to 70 terawatt year per year. So if we look our demand of 28 terawatt per year, we can see that wind can meet this demand, and if we can make a infrastructure based on wind, that world can be sustainable. But if you look on the solar availability, That is 23,000 terawatt year per year. And if you see the capacity in terms of bubbles, these bubbles are showing relative size compared to energy demand, energy needed. So this bubble will be like this. And that's why when it comes to the renewable energy or green energy, then there is no limitation. And I would like to bring a fact that our leadership is so visionary that International Solar Alliance, that headquarter exists in India, and India started this initiative around 8 years back. I don't know how many you know that, similar in line of IITs, IIM, and NITs, we are having our National Solar Institute, and they are located around India, and then the researcher from different stream, including electrical engineering, physics, and material science, and many other area. They are working on the next generation of solar panel and next generation how to harness the solar energy and how can be independent in terms of energy requirement. And then that is something which we engineer also not knowing fully. So my advice is, if you are having any interest in green energy and renewable energy, please go through these international solar Indian Institute of Solar Energies, which are they are started in different state, and then we are having our international headquarter in Delhi, International Solar Alliance. If you look on world's some of the biggest solar power plant, so most of them they exist in India. Whether it is Riva Ultra Mega Plant or Pavagada or Badla Solar Plant, they are in India, and we owning them. If we look as a whole on the growth of primary energy market from solar PV plant, this you can understand it with these colors. If it is uh, slaty color, then it's no data or 0%, but yellow 0.1%, and then if you are having pink, it is 0.8%, and dark red, then you are having 1.2%. So, but in this graph, you can see very well India is positioned very well, and it is having more than 1.2% of penetration. So and then the growth is continuous. That is phenomenal. As I stated earlier, that in next few years we will be self-sufficient in energy need, and already 60% is more than 60% is coming from renewable energy. That's a proud, you know, proud achievement for us. If you look on cumulative growth of solar PV plant worldwide in gigawatt, then this journey was started from somewhere 7 gigawatt in 2010, but there is phenomenal growth, and it reaches to more than 45, like 43 gigawatt. So these numbers, they should be more for last 2 years. And if you see the trend in the top 10 of total installation in market, percentage of total installation market. So the size means um, the, there is a tendency towards having uh, smaller size of plant. So it market share, which was around earlier 100%, that is going down to 70%. So there are more and more plant are coming, and then they are having equal power size. So there is no such you see number of 1 gigawatt market, and then out of top 10 in percentage of total market. That's this curve predict that. And why this is happening? Because solar photovoltaic multi-module prices there is a sharp decrease in these prices. So around threefold decrease happened between last 4 years, and it is further downing this curve. So you can assume that prices are going down, and India is also heavily investing around 30,000 Indian rupees, 30,000 crore Indian rupees are invested for next generation solar power plant, solar panels, and we are also doing this, technological advances and how to increase the efficiency of solar panel, and we are continuing working on that. When it comes to different type of renewable energy sources and how they are good in terms of carbon capture or carbon storage or carbon neutrality. We say the name carbon neutrality to compare each uh, renewable energy sources. So if we say a base station coal as 1 kilogram of carbon dioxide equivalent emitted for every kilowatt hour of energy generated by the conventional coal plant. In comparison to that, wind energy plant is only generating 10 gram of COT. So see 100-fold decrease in per kilowatt hour of energy by wind. But photovoltaic, they generate little more carbon footprint. They are 4 times of wind, but it's still 250 times or 25 times lower than the coal plant. Anybody can tell why this wind is much cleaner compared to photovoltaic? Because the carbon emitted during the fabrication of these photovoltaic panel, that is far, far greater compared to what is needed for making blade and total carbon footprint for installing the wind plant. So what are the recent trend in wind energy system? Wind energy conversion is the fastest growing source of new electrical generation in the world, and it is expected to remain same. At the end of 2010, the installed wind capacity stand at close to 200,000 megawatt, doubling since 1999, and it could reach close to 800,000 megawatt by end of 2021. World is observing growth rate more than 10% each year. And today's 5% of world electricity comes from the wind power. Please note that this is not the case for Denmark, because sometime it happened that we are running our full generation based on our grid based on the wind. And sometimes we need to curtail the wind power. So much power coming from the wind plant that we need to curtail that. And that's why when it comes to the green hydrogen, uh, this collaboration between India and Denmark is playing a great role where the brightest brain of both countries, they are working towards a sustainable solution of green hydrogen where prices will be less than $1 per kg. And that dream is not far away, because a lot of commitment is from both sides. And this company like Everfuel, they are also having very promising plan, like in next 3 year, next 3-4 year, they need to build around gigawatt capacity electrolyzers, and they need to provide the green hydrogen stations infrastructure for the hard to abate sector, like heavy duty trucks and buses. So these are number what I was talking about, and you see there is negligible growth until their footprint were almost negligible until 2000. But suddenly, world is more and more cautious, and then you see this exponential growth, which is going beyond 800,000 megawatt, and it is going further. Just a comparison. In India, we are having a big wind energy company, Suzlon, which is the backbone in terms of previous year and previous decade development, and they are having their R&D center in Germany. So they are having cutting edge technologies and developing the best of wind energy harness technology, and they are using this doubly fed induction generator technology nowadays. So earlier, for many decades, they were using thermalized um, this induction generator, and then the fixed frequency one and tied to the grid. So things like technological advancement, they are also moving at a fast pace, and India is no longer you know technology importer, but we are also contributing to the world with best of best technology when it comes to even for the renewable energies. So when we say that, what are the recent trend in wind energy system? Harnessing wind energy for electrical power generation is an area of great research interest, and emphasis is given to the cost-effective utilization of this energy resource for quality and reliable power supply. During the last 2 decades, wind turbine has been developed in size from 20 kilowatt to 12 megawatt, while even larger wind turbine are under investigation. A lot of different concept has been developed and tested. One important development is on the electrical machine, a generator, where new concepts also have been industrially implemented. Before moving to this part, I would like to mention here that a new trend comes in the wind park and wind plant, that we are generating power that is first converted to DC and then through converter and then using the long cables or connecting to the grid. And that grid is supplying to the data centers or big consumer of electricity. And these data centers, they are again, they need to install transformers and in between UPS, and in that's everything is in 500 megawatt on that range of central when we're talking about the data center situated in the Central Europe. And you know that this double conversion from AC to DC in the wind generator, and then DC to AC from the wind converter through power grid, and then power grid to again voltage conversion, then connection of power UPS, and then conversion from AC to DC. Assume how much power is lost during this process. So there is a trend, and there's already few data center exist inside the infrastructure of the wind plant. So wind plant base pipe that is made in such a way that the whole data center is located there. And you know that power supply to this data center is directly provided from the DC link of the wind generator. So this is a great innovation. And of course, there is a redundant supply coming from the power grid, and then power grid is there in case of any failure in or any breakage in reliable supply. But that is very rarely used. So this is one trend coming in the in the wind energy, where data center, they are located inside the wind energy plant, and it saved the way, and then we don't need to create the we load the grid or creating the complicated grid infrastructure with uncertainty of wind power supply. Then another example that is, I will I will come to that green hydrogen part later, but just to continue here, that how can we use these um, uh, wind plant for energy sustainability and then reduce for greater energy efficiency. So you can imagine that, but this is also that there are pilot plant are running on that concept that we instead of onshore wind plant, offshore wind plant, they are more common in Europe. And now we are talking about these offshore wind plant. They will equipped with the electrolyzer itself there, and instead of cable, we carry the hydrogen through pipeline. That will be more cheaper and more efficient. We can reduce the power losses in the cable, and we can reduce the power losses from conversion from AC to DC, DC to AC in the wind plant, and then later in the substation, and later at electrolyzer level, where again we need to convert AC to DC, because everybody know electrolyzer work on DC power supply. So there are a lot of dynamics going on, and and then this research trend is there that we want standalone wind plant who can feed directly to the data center, who can directly interconnected with the green energy sources and electrolyzers and provide the green energy. Then we get independent of the grid. In that way, the uncertainty of the load and demand that is inherent part of renewable energy, that is go away, and we are having a stable grid as well as stable supply of energy. So I was talking about what research trained in the wind energy system, and that mainly it is going on the machines, and then which machine use as generator. And if we see this comparison, we will find that how this trend is going on, but I will come in the next slide for that. Before that, there are some conclusion, like important issue for wind turbine is the efficiency. Efficiency is important when comparing different system, because losses reduce the average production by the wind energy converter and thereby reducing income. The various wind energy converter system that are able to obtain maximum power output for varying wind speed. Moreover, wind turbine and generator adaptation should also be taken into account. The generator choice is based on turbine size and wind class. So if we look on it, we see that this W-fed asynchronous generator that was introduced worldwide in 90s, and then world shift towards the this permanent magnet synchronous generator, direct driven or geared. So we increase the efficiency by a large number, but then we are talking about nowadays superconductor based generators, and then there were some pilot plant they are running in offshore near UK, and DTU, Denmark Technical University, they are supporting with Siemens such research investigation. And this is possible, because in synchronous generator, we are having our stator winding. They are stationary, and they can be cooled by special means, and then we can reduce the ohmic losses in the stator winding. And that way, we will have a great power quality. We are having efficiency at all load, and of course small, lighter, and we can also avoid the gear, and subsequently we can avoid the losses. So according to time management, I do have 10 minutes more, and then we will jump to our first assignment. So this slide is showing overview of green technologies worldwide. We see that here in the top left corner, we see the renewable electricity generation. And the major portion that is, you see that is hydro right now, which no longer, if you remember my previous slide where I compare all the renewable energy sources, and the availability of solar and wind is much higher than hydro. So although its ratio is higher here, but it's going to less and less in future. Then next comes 20% wind. Then comes bioenergy 8%. Then comes solar 10% and geothermal 1%. This renewable electricity generation or percentage-wise distribution that is going to change in coming year. We'll see more portion from bioenergy, solar, and wind. Here you can see the growth rate in this left hand down corner, this growth in renewable energy electricity generation, how this growth was going on. We see the biggest growth is going on solar, that is 22.7%. And then it goes with, with the wind 12%, and then it goes with the hydropower only 1.1%, and it going with 5.9% with bioenergy. So because the percentage share is small for this bioenergy, although growth is 5.9%, so it's still this total distribution, total, uh, total terawatt hour generated by these source, they look like this. And here you see that hydropower is almost stationary compared to in this comparison, but this growth is coming from these three, bio, solar, and wind. And that is our prediction also from our previous discussion. So if we look on the number, in 2019, it was around 7,000 terawatt hour total amount of electricity generated with the renewable, and hydro account for 61%, and wind, this was around 20%, 1,412 terawatt hour, solar around 700 terawatt hour, bioenergy around 600, and geothermal 92, and marine energy, which was not accounted here, that was 1 terawatt hour. So tidal, we are talking about tidal energy and other other means where we are harnessing the marine energy. We are building temporary, we are using tides to store the water and then use the hydro plant or similar arrangement. And bioenergy generation divided into solids biofuel, biogas, renewable municipal waste, and liquid biofuel. I am having an example from Danfoss Drive previously. You know that our top 3 city in Denmark, like Copenhagen, Aarhus, and Odense, they are energy neutral in terms of when they are doing the wastewater treatment. So by using correct methods and employing the correct or the cutting edge equipment where we are using efficient motor control, we are using efficient heat process, efficient aeration properties, and providing correct enzymes and bio boosters. We can clean the wastewater, and then on the same time we can generate this uh, this municipal waste which can be burned, and then although we consume electrical energy, but in the end this wastewater treatment gives enough heat energy. So in terms of total energy audit, it is energy neutral solution, and that's going very popular. And India is also working on that kind of solution where we can make our all the water pollutant get away, as well as we will get benefited, and then we are only one time investment on that, and then the later we can be energy neutral on that. So it's a big research area where power electronics can play a big role. And especially when we are talking about just a thought provoking thought for you guys who are the participant and interested in research, there may be green hydrogen also contribute here. You know, we are using when we are having electrolyzers, these electrolyzers are generating hydrogen or oxygen, and oxygen silently disappeared. Yes, we are not talking about oxygen. It's not the giving us proper cost. But imagine a location where remotely we use the wind and solar energy, and we install a big electrolyzer plant, and we use hydrogen for the energy. But the same time, this oxygen, additional oxygen, can be used for wastewater treatment or similar other applications. So there are some models are developing here in Denmark where there are different agencies, they are working together and then building an ecosystem where then most efficient energy system can be made. For example, when Everfuel is making electrolyzers, they make sure that all the heat generated during electrolysis process that can be fed to the district heating system, so that there is no wastage of energy. And in this way, electrolyzer is more efficient, as well as the throughput of the electrolyzer plant is higher, and then the cost of hydrogen per kg hydrogen, that is also reduced. So being said that, I think it's time for our first question. But before that, you need to be introduced. So what I will suggest, I will go for next 10 minutes for discussion, and then we delay this our break. Instead of 3:40, we will go break at 3:50. Okay. So we were talking about green hydrogen, green technologies, comparison of that, and then we move to the renewable electricity generation by region. We look here, and these numbers, they are quite interesting, and we can proud that Asia is leading in this green energy, renewable electricity generation. Of course, major share is from China, but India is also coping up, and India is also contributing here. So if you compare North America, that is 693, but 1812, terawatt hour generated from Asia. Similarly, Europe, that is 534, but that's around more than 3 times in Asia. And it's most of the energy is from hydro, wind, bioenergy, and solar and geothermal energy. So I was only comparing hydro energy part, but if you see the total part, this is a around 3,000 terawatt hour from Asia, and from North America it is around 1,250 terawatt hour. So more than 2 times. From Europe, it is 1334. So it's again more than 2 times from here. So Asia also accounted for most of the increase in solar generation, 77 terawatt hour out of the global increase of total 128 terawatt hour. So most goes to Asia. Growth in wind generation occur in Europe and Asia, that is 58 terawatt hour and 51 terawatt hour, followed by North America. So because Europe is situated in a, they are having geolocation that's supporting this wind for them. Um, this all the most of the European countries, they are surrounded by sea, and then sea is the main cause of for the wind movement, and that's this wind generation that's largely suited to them. We talk about in 2019, renewable hydro generation contracted in most regions, but expanded by almost 90 terawatt hour in Asia, is accounting for all growth in global generation. So after discussing these renewable energy and their growth and their market share, we again come to question, why green hydrogen? It was predictable in past that green hydrogen should receive a new wave of attention from government, policymaker, energy sector stakeholder, and even the general public. It was predictable, but there were some uncertainty. And I will come to that, how these uncertainties are go away now. An unprecedented number of report, news article, webinar, and event in last 2 years, they were touched upon the topic. But the development of green hydrogen sector is itself is still at a very early stage. Each year, around 120 million tons of hydrogen are produced globally, mostly from fossil gas and coal. So when we get fossil gas or fossil fuel, then there is a classification of hydrogen that say that black hydrogen. But when we are using coal especially, then we say that gray hydrogen, and which together account for 95% of global production. Hydrogen used for crude oil refinery and for ammonia and methanol synthesis represent almost 75% of hydrogen consumption. And now comes the reason. The, the geopolitics, role of geopolitics and European energy crisis that paved the way for faster transition towards the green hydrogen. You will be surprised that European Union last year they passed a resolution that by 2030 their total energy, 60% of total energy use will be only by green hydrogen. So now, real time development, the geopolitics and this energy crisis, Russia-Ukraine war, and many other things that created a need now from the policymaker side and from the people and from the also from the market side. So according to the roadmap, every country is having its roadmap. Most promising is most optimistic is India's green hydrogen journey, that where we want that $1 trillion green hydrogen economy by 2030. By 2050, green hydrogen need to have far greater dimension than today. Production reaching out for 400 million ton equivalent to 49 exajoule. Producing that much in turn would require a significant scale of electrolyzer, with total installed capacity growing to 5 terawatt. The electricity demand to produce hydrogen reaches close to 21,000 terawatt hour per year. Achieving these ambitious numbers will be a major challenge, but this International Energy Agency report described that this challenge can be met through a wide range of policies. Policymakers then have a central role to play and already have the tool to meet the challenge. Some countries have already introduced hydrogen strategy and implemented initial policies to support the sector, while new target policies are being drafted. Still, for the sector to move from niche to mainstream, more diffuse policies and measures will be needed. Policymakers today can draw early lessons from the trailblazing countries in green hydrogen sector and from their own experience of renewable energy policy making in the power, heat, and transport sector. So just to jump to hydrogen as an energy element, we see its melting point is 13.81 Kelvin. We know that 0 Kelvin 277, 273 degrees centigrade. So you know that it's almost 200 and how much? 73 minus 20, that is 53. So it's around 260 or so, minus 260, and it is around minus 253. That's the boiling point of hydrogen. So it become gas beyond that. And you see electronegativity is 2.1, ionization potential is 13.598 electron volt. This configuration, we see that it's non-metal, atomic weight 1.00794, and other things. Its density is 0.0898 gram per liter. That's very interesting. Please keep focus on this density, because our numerical questions, one of the numerical question comes on that. So if we classify hydrogen as an energy storage element, and we need to classify color of hydrogen. So this color signify that what is the source of this hydrogen origination, whether it is generated from fossil fuel. If it is from fossil fuel, including coal or gas, we generalize, we can name with the black hydrogen. But if it is a coal specifically, then we are saying brown hydrogen. If it is a steam reformation, then this is the gray hydrogen. If it is using nuclear power and electrolysis, then pink hydrogen. If it is using steam reformation, but that during the steam reformation, whatever the carbon footprint or carbon emission, that we capture that much carbon, then this is known as the blue hydrogen. So blue hydrogen is nothing. If we are doing we are during the process of gray hydrogen, brown hydrogen, or black hydrogen, if we can capture whatever carbon emission take place during this hydrogen generation, we capture that carbon and store that, then we can certify that hydrogen as a blue hydrogen. Then turquoise hydrogen. So if we are using methane pyrolysis, this is the chemical process by which hydrogen is generated, and then this this is this if the color of hydrogen is certified color is turquoise, then it is a methane pyrolysis based produced hydrogen. Please note that hydrogen is a colorless gas. You can't see any color on the hydrogen. It is only the certification. When you buy hydrogen or we consume hydrogen, then the certification comes with the hydrogen, and that certification will tell you what is the source of the production of this hydrogen. Because hydrogen cannot be available, it is not available like you can capture from the environment, or you can dig and get like a crude oil. So if we are using any renewable energy sources for electrolysis, then produce hydrogen is the green hydrogen. So and then most importantly, this if we are using the solar energy for electrolysis, then this hydrogen is yellow hydrogen. So green hydrogen cannot be yellow hydrogen, but yellow hydrogen can be yellow hydrogen and green hydrogen. You got my point. Now comes hydrogen as energy storage element. So there are three form of hydrogen, as I told you, below minus 253 degree centigrade or below 260 minus 260 degrees centigrade, or exactly the number is here. Uh, it is gas, liquid, but solid number is not here. But you see that for hydrogen, it is boiling point is minus 252.8 degree. Melting point they have not noted here, but energy density is 141.8 megajoule per kg. So this is the important number, and it is not changing when changing gas to liquid. Methane that 55.7 and gasoline is 44.4. So hydrogen is, how many times superior? 3 times almost superior to gasoline and methane in terms of energy density. But if comes to the energy density, volumetric energy density megajoule per liter, then we see that gasoline is having big number, because it's volume wise, it is a very rare gas and a very, you know, um, lightweight, 11 times lighter than air. So and it occupy more space. Specific gravity that is 0.07 kg per meter cube, and compared to gasoline 0.7. And please keep open eye on these numbers, because there were questions around this. So of course hint will be there, but you need to be focused on this slide. And then flash point, there is no flash point in hydrogen, but in gasoline there is a flash point at 13.3 degrees centigrade. And CO2 emission, we see the 0 for hydrogen and 111 gram uh, per megajoule, and here 148 gram per megajoule. So what we conclude, on a weight basis, hydrogen has a high energy density, around 3 times greater than most fossil fuel. This high energy density make hydrogen an attractive replacement for the fossil fuel, such as methane and gasoline. So that's the advantage we need to keep in mind, that 3 times higher energy density of hydrogen. Hydrogen has a very, very low boiling point, around minus 250 degrees centigrade. It's just 20 degree above absolute zero. Hence, it requires a lot of energy to convert the gas to a liquid. So if we want to bring back normally in room temperature, or even just temperature above than 253, it is a gas. So if from room temperature you need to reduce the temperature to minus 253 degree, you know that how much energy it consuming. So it's a very energy intensive work to convert hydrogen from gaseous form to liquid form. And liquidified hydrogen is currently used in special applications such as space mission. This is the very interesting fact, that if you look on the technology readiness level of space application, that is almost 9 to 10, because this liquid cryogenic technology and liquefied hydrogen use in rocket engine, that's reaches to highest level of technological advances. And we need to bifurcate to the lower niche application, like in buses, in car, in motorcycle, and in scooters. So it is not a big challenge in terms of technological adaptation, but of course it will take its own time. It's not the one day thing. So we say that in such cases, issue to do with thermodynamic efficiency are not critical. However, they become a serious concern when hydrogen being considered as mass market fuel. The specific gravity of liquid is low, hence its energy density on volume basis is only a third of value of gasoline and other liquid fuel. Quite interesting fact. When we talk about volume basis energy density, then it is one third of gasoline and liquid fuel. In round number, a tank of liquid hydrogen deliver only a third of energy of a tank of gasoline. This low specific gravity negate the effect of having high energy density on a weight basis. So what we get on weight basis, 3 times higher energy density, that is reduced to one third on the volume basis in hydrogen. So in all, it's negated. Hydrogen has wide flammability limit and low minimum ignition energy. These property create safety concern, an issue that will be need to concern. In fact, the hydrogen does not emit CO2, and it does not mean that it is not no greenhouse impact. When burned in air, the gas create nitrogen oxide, some of which are potent greenhouse gases. And itself, if we can release the hydrogen to atmosphere, it is having impact on the as a greenhouse gas. So if you look volumetric energy density of hydrogen in practice, you will find that volumetric energy density of gaseous hydrogen at atmospheric pressure is 0.09 kg per meter cube. Keep this number in mind. Consequently, under normal condition, much space is required to store gaseous hydrogen. Therefore, hydrogen is virtually not stored or transported in gaseous form at atmospheric pressure because it's simply not efficient. So, in never ever we will transmit or we take distribute from one place to another place, carry this hydrogen in normal pressure. We need to increase the pressure. At a pressure of 350 bar, the volumetric energy density of gaseous hydrogen is around 26.1 kilogram per meter cube. So by increasing pressure to 350 bar from our atmospheric pressure 1 bar to 350 bar, you see that it's around 300 times or more than that. We are having this volumetric energy densities increase. It's 00 and 300 times increase. This increased pressure make it possible to store considerable more gaseous hydrogen in the same space. The pressure of 350 bar is used in the tank of gaseous hydrogen trucks and buses, and even in, for example, the one from Hyzone, this is the company providing these trucks. A loaded 55-ton trucks need around 50 to 70 kg of hydrogen to travel 500 to 600 kilometers. At a pressure of 700 bar, the volumetric energy density of gaseous hydrogen is 42 kg per meter cube. You see that from 0.09 kg in 1 meter cube area space tank, you only carry 0.09 kg of hydrogen at normal pressure. But if you increase to 350 bar pressure, then you can carry 26.1 kg on the same space. And this further increase at 700 bar to 42 kg. But please keep your open eye here that it's not linear increase. It should be 52.2 kg per meter cube, like here, if it is a 350. So there is a loss of energy in compression. So that when we are transporting hydrogen, then there we need to calculate the suitable cylinder size, pressure size, and then we must be energy efficient also. It's not like, because this energy lost uh, during this compression. This relative high pressure is used among other the gaseous hydrogen passenger car Hyundai Nexo with a 125-liter tank containing 5 kg of hydrogen, and car can drive up to 600 kilometers. In liquid form and at temperature of 252.9 degrees centigrade, hydrogen has a volumetric energy density of 71 kg per meter cube. So if you reduce the temperature in cryogenic form, we can further even we can increase this energy density. Liquid hydrogen is also used as energy carrier for sustainable truck and aircraft, which are currently under development. And if we look on volumetric versus gravimetric energy density, volumetric, when we talk about kilogram per meter cube, and then gravimetric when we talk about megajoule per kg. And we distribute all the our fuel and energy fuel, then biodiesel, diesel, LPG, LNG, and natural gas. They are here in this range, but hydrogen, that you see that hydrogen is here. If you're increasing the pressure, storage pressure, or you're converting to liquid, still it is not, you're not getting advantage in volumetric comparison compared to other fuel. But our gravimetric comparison, that's very high compared to other fuel. That's the advantage. If you look on energy storage element like a lithium battery, lithium ion battery, alkaline battery, hydride battery, lead acid battery, how they place in terms of volumetric versus gravimetric energy density. So this location for battery is here, liquid fuel is here, and gaseous fuel is here. And among all gaseous fuel like propane, butane, acetylene, methane, hydrogen is having lower volumetric energy density. So kilogram per meter cube. So that is lower. when we are comparing with other batteries as energy storage element or liquid fuel. So thank you very much for your patience. Now we come for a time for exercise. And I propose that we get a break now and we come back for exercise later. What do you think?
Okay, sir.
So time is here. Dennis time is 4:53. How many minutes we need in break?
Uh, 5
10
minutes,
minutes?
not more than that.
5 minutes.
Yes,
Okay.
sir.
So let's meet at 5 o'clock. So your time is how much? 8:30. 8:30.
Yeah, it will be 8:30.
Okay. So let's meet at 8:30.
Sure.
Yes. So I'm back.
Yes, sir.
So let's recap that we found that hydrogen is a very good fuel for future. Not only it can support our energy need, but it can be a good contributor for grid stability and our energy stability. We have seen that volumetric density for hydrogen is poor, but its uh, energy density in terms of gravimetric uh, uh, efficiency that is higher. So now all participants, they are requested to look on this numerical. And problem is, how much hydrogen do I need in my car based on these data? Your car is equipped with the fuel cell and inverter, and then it's running at your fuel cell is maybe drive system that is running with a 51% of efficiency. And you need 8 hours to drive from Bhopal to Delhi. If the low heat value of hydrogen used in your fuel cell or in your car drive system is 120 megajoule per kg. So how many kg of hydrogen is required for a round trip? So question is clear to everybody? It's how many? So efficiency is 51%. Low heat value of hydrogen is 120 megajoule per kg, and you need to drive a car to reach from Bhopal to Delhi 8 hours, and you need to make a round trip. And hint, that is the simple formula which will give you this calculation. So you need to have your power here. How many power you want to use? In how much power in kilowatt? How many hour? Efficiency and LHV value. So how you will solve this question? Is there everything is available here or something is missing?
Missing, sir.
Yeah. What is missing?
Sir, power value.
Power.
Yeah. So let's take it's a 100 kilowatt. That is the power, and then solve this. Any idea how much hydrogen? 100 gram, 1 kg, 100 kg, 500 kg. How much is needed? Any number comes, any calculation, any calculator, given the result.
The hydrogen amount is 47058.82.
What? Gram, kilogram, milligram? What?
470 gram.
470 gram.
470 grams.
Can you check it one more time? Okay, let's do the step by step. Then you will see. So we are having 470 gram, one answer. And Miss, what you told? How much?
So 47058.82. So I'm
So
Sir, it's
are you doing like this?
470.58 grams only.
478 point.
470.58 grams is coming only.
Okay, 470.5 gram. Then something is wrong. Okay, so how we need to solve
Sir,
it?
40 kg.
40 kg. It's maybe reaching the value, but we are doing some mistake. But it's better than it's not. It's off, totally off, but it's coming in the range. Okay, can we do like this? How much hydrogen needed to run? That's number of hour. So this P is 100 kilowatt. You put 100 here. Okay, hour is 8 hour. Multiply 100. Let me do in my calculator. I also don't know the answer of this question actually because I changed the data. So let me do it. But so we can take 100 kilowatt. Okay, everybody agree? 100 kilowatt multiply by time 8 hour. That's also we agree. Multiply by 3600. Okay, and then we are having efficiency. That is how much? 51%. So we just put 51 here, and then how much is the low heat value? That is 120 megajoule per kg. So we put 120. So this capacity comes 470 what? 470 kilogram or gram? It's 470 kilogram.
Gram.
So how many get this 470 kilogram? Everybody.
Sir, LHV should be in kilojoule.
Which energy?
LHV.
That's yeah. You're right.
Sir, energy is given in 120 megajoules, so
In
we
the
need to
formula.
convert it in
You need to
kilojoules.
convert
That's
it.
why.
Yes, you're right. You're right. So it will be how much?
Sir, then it will be 470.588 grams only.
It is something somewhere we are doing wrong. I don't know where. Okay. Assume that we are with these number we are correct. But that's interesting is it's round trip, so you need to double it. So that's the answer. Okay, and we need to consider this efficiency of fuel cell, and this efficiency can be efficiency of electrolyzer also. Got my point? LHV of hydrogen, that will be the same. So if somebody asks you that the electrolyzer plant is running with such a efficiency and this capacity of electrolyzer plant is so many kilowatt, so how much hydrogen will comes out? So you can calculate like here. So how many hydrogen per hour if you keep it one and multiply by kilowatt by 3600 and divide by efficiency of electrolyzer, and so this way you can also calculate how much hydrogen is produced. Okay, so you got the idea? by a simple calculation, and you will get some value, and there will be some number. I don't know what is the exact number, because I have not calculated it before, but my from where I took this example problem, there something 94 kg was coming, but their power size was different, and it was only one way trip. So there were some changes. So we agreed that how it work. We have this here. We are having description to put it, and it's simple calculation. Now we jump to the very interesting property of hydrogen, that it is not an ideal gas. Everybody knows. So what is how it affect hydrogen weight per volume at varying temperature and pressure that get changed. So on x-axis, it is the pressure in megapascal, or pressure multiplied by 10 bar. So 1 bar, 10 bar, 50 bar, 100 bar, 300 bar, 500 bar, and 1000 bar. Are you with me? So this is the temperature, and this is the pressure, and this is the temperature from minus 255 degrees centigrade to 125 degrees centigrade. So if we take a number like 25 degree centigrade temperature, so at one this at normal atmospheric pressure, that is for 1 meter cube, it contained 0.0813 kg. But on the same time, if pressure is increased, it can carry 7.67 kg. And if pressure increased to 300 bar, it can carry 20.537 kg. And then if pressure goes to 1000 bar, then it increases to 49 kg. And please note that there is no linearity here. So it if and then increasing the pressure, we need to do the external. We need to drive the external energy sources. We need to use the compressor, or chemical compressor, or electrical compressor, and both places we need to consume some energy. And that way, it's not efficient, and there is a optimal efficiency comes with depending on the application, and depending on the temperature, and depending on the how much pressure we can carry. And now industry standard is 700 bar and 350 bar right now, and then for 350 bar refueling, 350 bar buses and truck and cars, they carry this mobile fueling station that can, or these storage tank can carry until 500 bar pressure, and with the 2.36 factor of safety for composite material type 4 hydrogen tank. So after this table, which is quite interesting, we are going to use in next numerical. We are moving towards what is the production and value chain of green hydrogen. So here is the renewable energy. We are using renewable energy, and we are using electrolyzers, and this electrolyzer technology can be solid oxide, can be PEM, or can be this alkaline electrolyzer. PEM means proton exchange membrane, and then transportation that can be done by storage in tank, by dedicated pipeline, or by hydrogen carrying trucks, or it can be transported by shipping. Then after transport, the next stage is production of green hydrogen. That's a transformation. So we can transform to e-fuel, or so we can generate synthetic fuel, or we can generate ammonia, or we can generate methanol. And then in end user, it can be industry. I told you, steel industry, chemical industry, fertilizer industry, refineries, they are consuming most of the hydrogen. And in transport sector, this shipping, aviation, cars, rails, there is a now major tendency. There is a greater tendency in Europe, especially in Germany. Their goods train, they are using hydrogen to run the fuel cell based engine. and then trucks and buses. And this hydrogen in end use can be used in the heating also. And last but not least, it can be again fed to the fuel cell and generate power, and that power will go feedback to the grid, or the cycle is complete. So it's very important that we will talk about levelized cost of hydrogen. Do you know that? How can I keep this display into back? So this is the levelized cost production model, and this model is developed by comparison of OPEX and CAPEX, especially the cost of electrolyzer and cost of operating costs by means of electricity. So if we can reduce electrolyzer system cost from 770 US dollar per kilowatt to 200 kilowatt, then 200 US dollar per kilowatt, you see that price goes quite down, and then they can be come in the bracket of 1 to 2 US dollar per kg. And in this analysis, electricity price was keep constant US dollar 20 per megawatt hour. But on the other hand, and then in order to reach this bracket, you need to run around 2000 hours your electrolyzer plant with the full capacity. But on the other hand, if you are assuming electrolyzer system cost is $200, and on top of that, your energy prices is reduced from 20 US dollar per megawatt hour to 10 megawatt hour, US dollar 10 megawatt hour. Then you see that you can achieve this target way before running, 2000 hours. It can be achieved within 1000 hour or less. And then price also going very with the reduced price of electricity and optimal price of electrolyzer plant, it can go further down way below $1 per kg. And these are the production model. When we are on-site production, we are doing with renewable, then it's green and it's green energy based hydrogen production, but it can be with the grid, power grid, and power grid cannot be you need to certify the energy use, that this is the green energy use, or this is the conventional power, coal base, or conventional power generation. So there is a mix, and then you need to certify that hydrogen is green or not. But in third case, then your grid will provide you power as per your need. So although it equipped with both, but you are only interested in green energy. So either you will use your own green energy, or you will ask that your energy provider can provide you energy based on green availability of green or conventional energy. So there are three models: one full on-site production, one electricity from the power grid, and third one is you are having your on-site production, but you are supplementing it with the grid. This is the hydrogen role in energy transition, that how can source of energy, so you are having in our large scale efficient renewable energy integration. So with hydrogen, you can develop infrastructure where you are having all the renewable energy sources. They in turn generate hydrogen, and then you connect them through hydrogen. So and then you distribute energy across sector and region by means of different model like piping, by truck, by shipping, and a dedicated corridor, and act as a buffer, so you can use them to increase system resilience. So you have temporary storage, and with the fuel cell base, you can have non-interruptible power supply, and then this way you can um, make your grid resilience. And then in the end use, we can use this green hydrogen transport sector to decarbonize the transport sector or the industry use. There we can reduce the carbon uses and serve as feedstock using captured carbon. So when we are generating, we need to produce urea or methanol, then this green hydrogen act as a feedstock, and then help decarbonize this building heating. Instead of burning fossil fuel, we can use green hydrogen there. This is showing correlation between levelized cost of hydrogen and operating hour of grid connected electrolyzer. So you see that this loading capacity factor 0 to 100%, this increases like this, and levelized cost, you see this if capex and opex, they as per the capacity factor, they get um, reduce. So your capacitor infrastructure, if your capacity factor is increased, it gets reduced. Similarly, if your OPEX is increases but slightly based on the your capacity utilization. And your and then wind share, you see that if it is wind share from 80% to 60%, and in this way you see the effect of your levelized cost, and this levelized cost in US dollar per kg, how it varies. And here you see the green hydrogen production CO2 benefit. So if in existing gas pipeline, you introduce green hydrogen for, for compensating carbon dioxide emission. So instead of, just for example, how the cost and CO2 benefit is there, if you are introducing 7%, you're reducing your natural gas by 7% and adding hydrogen 7%. Then you can have this benefit in gas emission from somewhere 55 to 50%, so 5% increase. But the price, your cost of the system, that can increase 37%. This might be reduced now because gas price is increased, but on this model, we can say that the cost benefit is not directly proportional, it is manifold, many times compared to it. So here is the 5 times extra cost we need to pay. So then in the end, we are reaching to this again. I'm showing this, and with the clear message that window of opportunity is closing fast for any meaningful action. And then we can also say that mobility sector is one of the main culprit for present day climate issue. And in this mobility sector, hydrogen with the mobility technology, it is having tremendous potential to compensate these carbon emission. And here with the different TRL level, we see that space travel that is reaches to 9 TRL level. Industrial trucks, they are on 8 to 9 level. Stationary application, they also reaches to 8 to 9. And then passenger car, they are around 8. Light rail, there is something, there's like 7. Aviation, that is still need to grow. We are having some technology gap. Shunting loco, they are around 6 to 7 TRL level, and shipping is there is a technical gap there. And then motorcycle, as I told earlier, I touched upon the motorcycle and lorries, they need to increase their TRL level. So there are considerable effort are needed to meet this technology gap and to use this H2 in green H2 in mobility sector. This is the full value chain utilization, that you're generating hydrogen here, green hydrogen, and then you are consuming it here. But on the same time, you are having a way to interconnect with smart storage, connect with the fuel cell, and then you connect this um, uh, seamlessly. This smart has to full value chain, so that you are having zero carbon emission and zero carbon dioxide generated from environment. And this is one way where we are integrating industry to the power stations. through green hydrogen. And then for smart H2 for the future, that will be hydrogen has the potential to fuel the economy while emitting little but clean water. And we are at a leading edge of hydrogen revolution. The world must finally tap into hydrogen potential to play a key role in clean, secure, and affordable energy future. FCVs, they are powered by hydrogen and are most efficient than conventional internal combustion engine. Hydrogen power fuel cell electrical vehicle emit none of these harmful substances. Only water is a product, and hydrogen is a real option for diversifying our transportational energy option while at the same time reducing pollution. So this is a Hazel model of hydrogen and zero emission logistic, where we see that dissemination of how this we can go from production to application while considering the sustainability and safety during this process. There is a model from this Belfast Metropolitan College where how they work with transfer of skill, dissemination of knowledge and communication. I will skip this, and then these green hydrogen based city buses, they are reality now, and then world is moving towards that direction. There are many players who are making this. And now time comes for next exercise, and we are having 5 minutes. So now my next question is, how many type 4 hydrogen cylinder do I need to buy? I'm having a type, I'm defining a type 4 hydrogen cylinder under a pressure of 300 bar, contain approximately 7 kg of hydrogen. How many hydrogen type 4 cylinder will require to store 103.1 kg of hydrogen at 500 bar? And my hint is here, use following table and calculate. So 5 minutes for you to exercise it. It's simple. We are engineers and everybody use the steam table in the first year engineering course. It's kind of that application. So hydrogen with different pressure and different temperature, how is weight is change. So if we want to store the hydrogen with so carrying weight will be changed with the pressure and temperature. And we know we are having 103.1 kg of hydrogen, and that should be stored at 500 bar. So how many type 4 hydrogen cylinder are required? Any doubt on this question you can ask? No doubt? Can you see this table clearly?
Yes, sir, it is visible to all, although.
Okay. I'm giving first hint. Assume 25 degrees centigrade temperature.
We can leave it to the participant.
Okay. So nobody is trying to solve it or any interest to solve it. So I can give you, it's a damn easy question. Anybody interested to know the answer? How many cylinder? See, you need to define the temperature and pressure first, because we know that this gas changes its under pressure, it changes the uh, energy density and volume density and everything. So at 300 bar, you see here at 25 degrees centigrade. At 300 bar, this is here, it is containing 20.537 kg per meter cube. Okay. And if pressure is increased to 50 bar, it will contain 30.811 kg meter cube. So the same cylinder which can contain 7 kg of hydrogen at 300 bar, it will contain 7 multiplied by 30.881 divided by 20.537. This much hydrogen, and that might be coming around 10 kg or something. And then now you know that at 500 bar, our one cylinder, this same type 4 cylinder can contain 10 kg, and then you need to store this much gas. So around 10 cylinder you need for storing this gas. Everybody is with me?
Yes, sir.
Yes,
Okay.
sir.
Okay. So this way we can calculate it, and it's quite interesting. And some of you will join the hydrogen industry, then this might be some calculations are needed, and this table might be, you must have maybe 1 or 2 row in your head. So we need to, being a technology manager, sometimes we need develop some product, and then we order to the supplier Hexagon or this Enrox and Hanwha, these suppliers around the world, and they are having different pressure and different composite material, and then whether we can transfer the gas through our trucks using those cylinders. So these are the practical question comes, and that's why I ask you. And now, as a closing remark, we are going very close to the time, and I will not take much time, but I will show you this model, energy dispatch model, where we can consider transmission infrastructure, generation technology parameter, plant nameplate capacities, hourly load profile, fuel cost, intermediate generation profile, and then hourly supply and hourly demand. Then in output, we can give the hourly grid operation, hourly this hydrogen energy storage operation, storage capacity, electrolyzer capacity, fuel cell capacity, H2 fuel cells, hydrogen fuel cells, and greenhouse gas emission. And so this model is very similar to our power trading model, but here the input and output is in terms of hydrogen infrastructure. So from here, you assume a situation where we are having our power grid, and parallel to that grid, we are having hydrogen pipe or hydrogen gas network, and there we are, and we are all the electrolyzer plant are connected together. So instead of connecting the renewable energy sources to the power grid, we can decentralize it, and we can connect the electrolyzer plant to produce the hydrogen, and then the rate of production of this hydrogen, that is governed by this energy dispatch model. And then different these um, electrolyzers, they be maybe 500 megawatt, 1 gigawatt, whatever the size, and they spread around the country, but they connected through, their output is connected through the um, hydrogen infrastructure or pipeline, or with dispatch in terms of trucks. So that way we can maintain stability in energy generation and maintain the renewable energy sources, and we can have this greenhouse gas emission control, as well as we can offer the this green certificate to the customers, because in coming year that will be a requirement from the policymakers that industry should compensate their carbon emission by a certain percentage. So not taking too much time, I will conclude here what need to be done, focusing on these three rudiment: that zero carbon generation, increasing stock of fuel cell electrical vehicle, and subsidized capital energy storage project that will help us to decarbonize the world. And certainly this will help to establish an environment favorable for a more market driven shift in energy management, and a high penetration of intermittent renewables provide a surplus of zero marginal cost generation that can be leveraged to generate hydrogen at a competitive price to other fuel. Final remark: we have seen that there is a mega trend green energy towards green energy shift. Innovation in green hydrogen technologies, system level approach gives the greatest benefit, and harnessing advantage of full value chain of green hydrogen is as essential component in the success journey of green energy transition. Being said that, I must thank you all for your patience, and if time permit, I'm open and available for your questions. Dr. Sanjeev,
Yes, sir.
time for, if time permit, because participants are waiting for their exam, but if they are having question, they can ask one or two question. Okay.
Yes, if there is any question, any participant wants to ask, please ask the question, because we are having only a few minutes. At 9:15, we'll be starting the test. So anyone? Maybe there is no question, because this topic is totally out of the syllabus, maybe for most of them. Because hydrogen, till now, they have not even gone through these details. So once they go through these details, definitely they may have some questions related to hydrogen fuel. Because by now, everybody is talking about the battery and ultra capacitors and other means of storage. So hydrogen was the first time discussion. And if anyone is having any query, any kind of query, you can ask.
I have a general query.
Yeah.
Sir, with the hydrogen fuel, there is a major issue with the pressures. So how we will deal with that?
Can you just make broader? What are your concern with the pressure? How you see the question? I don't understand your question. Can you
So
make
actually,
broader?
my doubt is that when we come to the vehicle or any transportation system with the fuels, when we talk about the hydrogen fuel, then we know that hydrogen is stored in very high pressure system.
Mm-hmm.
So it may be risky for the traveling.
No. See, this pressure thing, it is not a problem, because we are our industry is handling these pressures for 1,000 bar or more than that. There are many applications where these pressure are tolerated, and the equipment are there. There are certain solenoid valve, and controlling these flow and accurately measuring the flow, and this is something which is well already in some application, like in these industries, when we are handling some these chemical processes, there we need to handle with this pressure. Problem is pressure is not a problem is we need to develop storage tank which are lightweight, because for stationary application, steel tank, that's not a problem. But when we are talking about carrying the hydrogen in trucks, there in mobile units, that's the biggest problem. How can we develop lightweight storage tank? But in the end, this for fuel cell, or for in when we are using hydrogen storage chambers, that's not a problem. That's the industry is well equipped with it, and they can come up with they already solution exist, so that's not a problem. Are you with me? You got the problem? What is the problem? Problem is
Yes,
from
yes.
type 1 storage cylinder, which are the steel cylinder, to reach to composite. Right now, even in the type 4, we are using two type of material, and their weight is, in order to store 10 kg of gas, the cylinder size is cylinder weight is 100 kg. So that is the challenge. If we can reduce this 100 kg to 20 kg, 30 kg, then it will be like a very good, very nice situation. Yeah.
Okay, sir.
Any
So
other
I
question?
think, yeah, I think there is no question. So we sum up this session. Thank you very much, sir. On behalf of the organizing committee and MANIT management, we thank you for sparing the time, and you have spared a lot of moments. Means we can say that almost 2 hours here, and maybe preparing the lecture beforehand. And it was a nice introduction of the topic, because we were targeting to have different topics during all 5 days, and fortunately we got all the experts who have touched many areas, not overlapping. So students have got a very good opportunity to get different aspects of energy storage, and this hydrogen fuel and hydrogen storage was one of the area which nobody has touched. So thank you very much for giving us this opportunity to listen you, and we hope that we'll have same kind of interactions in future also. And whenever you visit India, we'll have the face-to-face interaction in the institute, because now we are in the offline mode mostly. So once again, thank you, and nice to be with you always.
Thank you so much, Professor Chauhan, and I must thanks to again to my student who uh, carefully listened to me and interacted, and then the opportunity for speaking, and connect with you in future. Thank you so much, and bye.
Thank you, sir.
Thank
Bye.
you, sir. Thank you so much for this lecture, and it was really nice, as this hydrogen fuel is maybe the era for the electric vehicles, fuel cell, as well as this hydrogen based vehicle we may realize in the coming time. So thank you, sir. Thank you for your precious time.
Thank you so
And,
much, Dr. Salin. And
yeah.
it's the same warmth I also reciprocate. Talk to you later, and take care.
Yeah, sure,
Bye.
sure,
Bye.
sure. Bye.
Bye.
Thank you, sir. So all the participants, please be with us, and
Okay,
Dr.
sir, are you
Mukesh.
there?
सर
Yes, Dr.
लिंक
Mukesh.
यहीं पे शेयर कर दें चैट बॉक्स में।
हाँ,
हाँ,
आप
chat
शेयर कर दीजिए, कर
आप
दीजिए।
व्हाट्सएप पे भी सर डाल सकते हैं वो शैलेंद्र।
हाँ, आप शेयर करो तो मैं व्हाट्सएप पे भी शेयर कर दूंगा। आप इसमें डालो चैट बॉक्स में।
सर को दी थी मैंने, मैं इधर भी शेयर कर देता हूँ।
हाँ, चैट बॉक्स में डालो। So it is compulsory to all. It doesn't matter like you are MTech student and you have not registered for this. It is not a kind of thing.
So now you can open this and please start the test.
I have shared it on the group also, ATAL FDP group.
Here in the chat box you can see.
टाइम कितना रखा है?
Half an hour sir.
अरे बहुत ज्यादा रख दिया।
Okay sir.
Okay, please try to solve it as soon as possible, because there are only 25 questions and maybe you can solve it within 10 minutes. Let us see. ठीक है, आधे घंटे बहुत है।
So if you have any problem to open this, please let me know.
Yeah, we
सभी
are
लोग
here.
खोल पा रहे हैं इसको, ओपन कर पा रहे हैं सभी लोग? एनीवन इज फेसिंग एनी इश्यू? कैन यू कंफर्म?
So it's openable.
हाँ
बस ठीक
ठीक।
है, तो आप लोग शुरू करें.
Okay, no problem.
एनीवन इज फेसिंग इशू?
नो नो नो, नहीं है.
ठीक।
सभी को हो जाएगा, ओपन हो जाएगा.
Sir, I'm not able to see the link.
चैट बॉक्स देखो पूजा, आप चैट
यहाँ
बॉक्स
चैट बॉक्स आपको विजिबल है या इफ यू आर इन द ग्रुप?
ग्रुप में नहीं होगी ये सर।
चले,
एमटेक
आप
No,
आप
sir.
दूसरे ग्रुप्स में शेयर कर दो ना इसको.
Chat box not visible.
इनको पर्सनल भी भेज सकते हैं व्हाट्सएप पे अगर नंबर है किसी के पास.
नहीं, मैं ग्रुप में शेयर करता हूँ, एमटेक
चलेगा,
वाले
आप सारे ग्रुप्स में शेयर कर दो, जितने भी ग्रुप्स हैं ना, प्लीज शेयर इन ऑल दस ग्रुप्स. एमटेक के जो भी ग्रुप्स हैं उनमें भी शेयर कर दो आप.